Hello, today we look at the algebra of functions and composite functions. To begin, the algebra of functions involves adding, subtracting, multiplying, and dividing two functions. We will be asked to evaluate these functions for different values, input values. And so take a look here at the first example. They've given us the f, g, and h function in the form of an equation, and now they're asking us to perform different operations. So finding f plus g of 3 is equivalent to finding f of 3 plus g of 3. The 3 represents the x value that you input into the f function, so we have the square root of 3 plus 1. Inputting this into the g function, you would have 3 squared minus 2. You then simplify to get an output of 9. So f plus g of 3 is equal to 9. You would do the same thing with subtraction, just remembering to put parentheses so that you subtract all of the second function. Division, you would find the f of 0 first, so you have square root of 0 plus 1. Then g of 0 would be 0 squared minus 2 in the denominator, and you simplify to get a negative 1/2. Now take a look at problem number 11. Same question is being required of us, but this time instead of giving the functions in the form of an equation, they give them to us in the form of a graph. Notice the f function here in red is labeled. The g function here in blue is labeled. Remember, when you say f plus g of 0, they are giving you the x value and you are looking for the y value on the graph that corresponds to it. Let's take a look at f minus g of 2, which is equivalent to f of 2 minus g of 2. So looking on the red graph at where x equals 2, I notice right here that that corresponds to a y value of 4. Then looking on the blue graph at where x equals 2, I see that that corresponds to a y value of negative 4. So 4 minus negative 4 gives us an output of 8. Let's take a look at f times g of negative 1. On the red graph, the f graph, looking at x equal negative 1, the output here where I'm pointing is negative 2. On the g graph, looking at where x equals negative 1, the output here is 5 for the y value. Multiplying those together, we get negative 10. In this next example, they want us to find the intersection of the given intervals and then graph our set on a number line. So what I did was graph each part individually and then look for where they overlap. Look for what they have in common, and that would be our final answer to turn in. So for example, this first one I shaded the entire number line, negative infinity to positive infinity. This second part here, we shaded from negative infinity to 3, but not including the 3. If you merge these two number lines together, where would they overlap? Do you agree it would be from negative infinity up to 3, but not including the 3, because the 3 is not included in both graphs? And so my final picture could be this second one right here, and here's the interval notation to show that. Take a look at number 16. We have from negative 8 to 5. Notice the open dot and closed dot correspond with the parenthesis and bracket here. Then we have from negative 12 to 3. Where would these two overlap? From negative 8 to 3. And so we have that for the final graph here. Notice the open dots because the negative 8 and 3 are not included in both graphs. And there's the interval notation. The next thing they would want you to do is actually add, subtract, multiply, and divide the two functions in the form of an equation, and then determine what the domain would be of the new function you created. It would have to only include values for which the individual functions were defined as well as the new function that you've created. So remember, the domain is the x values, the input values. And pretty much we would say all real numbers most of the time. The exception comes when the function contains a fraction with variables in the denominator. Our concern is that we don't want to include any values that would make the denominators equal to 0. That would make the problem undefined. And also, if the problem has an even radical in it, we want to make sure we don't include any negative values underneath the radical sign because that would generate an imaginary number. We want to keep the values under the radical sign greater than or equal to 0. So looking at these individual functions, notice in number 21 and in number 23, neither function has a fraction, neither function has an even radical. So notice that I wrote all real numbers for each and every individual function. However, in number 25, this first function has a fraction with a variable in the denominator. So we would have to restrict the value that would make it 0, which in this case is x equals 0. We are saying you can allow all other real numbers, just not 0. If this had been my function, I would have to figure out what would make this denominator 0. So by setting it to 0 and solving, I see that I would have to restrict x equal -3. Everything else would be allowed except -3. In the g function here, we want to keep the radicand greater than or equal to 0. So we take it and set it greater than or equal to 0 and solve, discovering that x then will have to be greater than or equal to 1. So that represents the domain for that function. Taking a look at the examples that we have here, if you were to divide number 21's f function by the g function, this is what you would get. Whenever it's possible to factor and simplify, you would do so. In this case, there's nothing else to simplify. So this is what we would turn in as the quotient of those two functions. Now we have to determine the domain. Well, the individual functions allowed everything, but the new function we've created now has a fraction in it, and so we have to make sure to restrict anything that would make it 0. What would make this denominator 0? If x was equal to 1. So we restrict that from the domain. Notice the number line shows everything shaded except the number 1. My interval notation looks like this. Number 23, if we found the quotient of these two functions, this is what it would look like. When I factored the denominator, I realized I couldn't cancel anything, so this is what I would turn in as my final answer representing the quotient. Now, individually, they could accept all real numbers, but now that the new function has a fraction with variables in the denominator, we have to restrict values that make it equal to 0. And those values would be x equals 0, x equal 8, and x equal -2. So notice on the number line, I have open dots over those values. Everything else is shaded, everything else is acceptable as values to plug in for x. So notice the interval notation comes right from the graph showing what is allowed. In the final example, number 25, we show all four operations. The sum of the two functions would look like this, f function plus g function. The domain now, where would these two overlap? This one says everything except 0. This one says only from 1 to infinity. Well, the overlap then would take place from 1 to infinity. Same thing happens with the subtraction and the multiplication. When we look at the division of these two functions, notice the f function divided by the g function, we create a complex fraction. We can simplify this complex fraction by multiplying the numerator and denominator by the common denominator of x. What happens here is the x's cancel and you get 1, and on the bottom you get x times the square root of x minus 1. So this is the new function. Our domain, again, we're looking at values from 1 to infinity. However, we have a new thing to take a look at here. We have a new denominator that we haven't had before. This denominator has a square root of x minus 1 in it, in addition to just the x. So we know that we can't allow x to equal 0, but now we need to make sure we don't include anything that would make this portion of it equal 0. So take the x minus 1, set it to 0 and solve, and you recognize that 1 is not allowed because it would make this portion of the problem 0, making the denominator then 0 and undefined. So here's our domain for the other operations, but now we're going to have to restrict the number 1 from our domain. So the parenthesis shows that the 1 is not included. Now we're going to take a look at a new operation called composition. The symbol for it is a small open circle. When you see this, it is read as f composed with g. And so what you are doing with composition is you are literally plugging one function inside of the other. The first function labeled is, or presented, is the outside function. The second one is the inside function. So notice here they've given you the f, the g, and the h function that they want you to use. Looking at number 36, it says g composed with h. So we can write it like this: g composed with h of x. You are literally plugging the h function into the g function. So notice here, this is the h function. We are taking it and plugging it into the g function where there is a variable x. And so this is what we end up with. 2 over the h function, square root of x plus 3 plus 1. Taking this and plugging it in here where the x is. That is what the composite of those two functions would look like. Now we have h composed with g. So we're taking the g function and plugging it into the h. So going in reverse, taking this and plugging it in right there where the x is. This is what you would end up with. You could then simplify this a little bit by finding a common denominator, which right now the denominator on the 3 is simply a 1. So the common denominator would be x plus 1. So you would multiply top and bottom by that. Distributing through the parentheses, you'd get 3x plus 3. And so this way you've presented it as a single fraction. So this would be h composed with g. And then finally, number 40, you have g composed with g. So you're plugging the g function into itself. So notice this is the g function. We're taking it and plugging it into the x here. So you have 2 on top, and then where the x is, notice we've put the entire g function right there, 2 over x plus 1, and then the other plus 1 right there. This creates a complex fraction. And so again, we can simplify it by multiplying the numerator and denominator by the LCD, the common denominator, which in this case would be x plus 1. So you multiply the top and bottom. On top, you're going to need to distribute. On the bottom, this x plus 1 cancels here, but then you have to multiply it by the 1 that is there. So we bring down the 2, and then 1 times x plus 1 gives us this. Combine the 2 and the 1 to get 3, and here's our answer for g composed with g. How do you find the domain now of these composite functions? Here's a 3-step process that you can use. There is more than one way, but here's one of the processes. Number 1, find the domain of the inner function. 2, find the domain of the composed function, your final answer. Then number 3, find the intersection of step 1 and 2. So taking a look at f and g, the f function's domain would be all real numbers. There's no fraction, no even radical. The domain of the g function would be everything that would keep the radicand from being negative, right? So we would say x has to be greater than or equal to 0, since we have an even radical. Now, if I'm finding f composed with g, g is the inner function. So notice we take this and we plug it into the f function and square. And so the square root of x squared would be just x. So this is my final answer for the composed function. Now let's find the domain. So the domain of the inner function g, we said, was x greater than or equal to 0. The domain of the f function, the f composed with g, which is the composed function, looks like this. It has no fraction, it has no even radical, so we would say the domain is all real numbers. So now what is the intersection of x being greater than or equal to 0 and all real numbers? The intersection would be from 0 to infinity. And so that would be my final answer to turn in for the domain of this composed function. G composed with f, the inner function now is f. So you're taking this and plugging it in here. You would get the square root of x squared, which is x. The domain of the inner function, following these steps, remember, is all real numbers. The domain of the composed function, which is this here, has no fractions, no even radicals, we would say is all real numbers. So now, what is the intersection of these two answers? All real numbers. So this would represent the domain of our composed function, g composed with f.